Okay, to this point, we have talked about settlement at time equal to infinity, but we haven't talked about what's the settlement at 10 years, what's the settlement at 15 years, etc. So we're going to try it. We call that the time rate of settlement, and we're going to answer the question on how do we determine the time rate of settlement. We're going to consider two situations. Situation one, is this one. Situation two is this one. What's the difference between the two? Well, situation one is called double drainage. That is where I have a sand layer above and below the clay layer. It's called double drainage. It could be a gravel layer above and below the clay layer, but in other words, layers that water can drain into. So that when this clay gets squeezed, the water comes out of the clay, well, the water can go up into this sand, or it can go down into that sand. The thickness of the clay, again, we're going to use as H. And we're going to come up with a new symbol called HDR. If I have double drainage, HDR is H over 2. Why is it that? Because HDR represents the longest that a particle of water has to go to get out. So the worst case particle is in the center. It can go up, it can go down, but the farthest that point has to travel is H over 2. So HDR is H over 2 for double drainage. For single drainage, we have sand above, rock below the clay. That means that the worst case particle is at the bottom of the clay, and it has to go all the way the full distance, H, to get out into the sand. So in that case, HDR is H. Single drainage. Sand above clay, rock below. Again, it could be gravel above the clay. It could be silt instead of clay. The key to solving these problems, again, is getting the U excess. If we can get the U excess, we can solve these problems very easily. We have to go back to how we analyze these problems. You know, we had t equals 0 minus, t equals 0 plus, t equals infinity. So let's look at those, and then we'll talk about the in-between stages. So let's look at this particular situation here. Here's my t equals 0 minus situation. It's a double drainage because I have sand above, sand below. So in all these problems, the first thing you have to look for is it single drainage or double drainage. Then at t equals 0 plus, we apply our gravel fill. What do we know about the excess pore pressure everywhere in the clay at t equals 0 plus? Well, we know that the excess pore pressure, I'm plotting it here, this is the top of the clay, this is the bottom of the clay, and I'm going to show my U excess jumping from 0 to, and what is the value that it jumps to? Well, we know what it is because that excess pore pressure is equal to the stress caused by the fill. Stress caused by the fill, I'm just going to call it sigma. So that means that at t equals 0 plus, everywhere in the clay layer, from the top to the bottom in the middle, the excess pore pressure is sigma. Now, what happens as time goes by? Well, at t equals 0 plus, this is the same plot, I get the sigma, but then what happens? The pore pressure dissipates. And it dissipates in this shape. As time goes by, it dissipates. Oops. So as a little bit of time goes by, I get a shape of dissipation like that. As another little bit of time goes by, the shape of the excess pore pressure, that is like that. Until eventually, it keeps going lower and lower until basically it gets to Uxs equals 0. As we know, at t equals infinity, Uxs is 0. So here's Uxs is 0, here's Uxs is sigma. Those are the values at t equals 0 minus, t equals 0 plus, and then at in-between times, it takes a shape that looks like this. Why does it take a shape that looks like that? Why is that the shape? Because the excess pore pressures, near the top and the bottom, dissipate quickly. Why? Because they're so close to the sand. So I get very quick dissipation, excess pore pressure dissipation at the top and the bottom. And okay. So this is what we're trying to learn out of this, is the Uxs curves. This, you need to understand the basics of that. In other words, okay, that shape makes sense. That's pretty much all you need to know. If it makes sense to you, and it should, that's all you need for the time being. This problem has been solved. We don't need to solve it again. And the solution is in curves, standard solution curves. I'm going to give you the solution curves for a quiz. And so these are the excess pore pressure curves. This is the bottom of the clay. This is the top of the clay. This is the middle of the clay. And these are the excess pore pressure curve shapes for intermediate times. In other words, this is 100% of sigma, of the fill stress, 100% of the fill stress. And then as we plot this is 50% of the fill stress. We need to create a variable to help us. It's called capital T, dimensionless time. And I'll show you how we get it later, but for the time being, I want you to memorize that it's C sub V T over HDR squared. What does this mean? So first of all, C sub V comes from a lab test. You did that. So C sub V comes from your lab tests. Small t is the time in years. So in other words, do I want the settlement at 2 years, 10 years, 20 years? That is the small t that we're referring to. HDR, we know, is either H or H over 2, depending on whether it's single drainage or double drainage. C sub V, coefficient of consolidation. And the units are square feet per year. Those are the units you got. I can look at this, I'm going to plug in, I want to look at the units for capital T. C sub V has feet squared per year, small t has years, HDR is feet squared. What happens to the units? They all cancel. So it becomes capital T has no units. We call it dimensionless time or time factor. And so what we're going to do with our method is we're going to convert a small t, say of 10 years, to a capital T of 10 years, And then we're going to choose which curve to use for our solution. So once again, the small t will be given. We're going to, because that's the point, that's the time of interest for us. The capital T we calculate. And then we use that capital T is going to guide us to which curve do I use in my standard solution plot. This is what the standard solution plot is, so these are the actual numbers. This is capital T is 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, etc. This represents 1.0, that's the full fill stress. That's, half of the fill stress. And what we recognize is this is the bottom of my clay layer, this is the top of my clay layer, this is the middle of my clay layer. I just need to get a grasp of the meaning of this excess pore pressure plot. Again, this is the same plot. Sometimes it's plotted upside down. I don't like it like that, but you'll see it sometimes written this way. Same thing. The one thing I want you to notice is that when capital T is approximately 1.0, then UXS is very small and settlement stops. So people just like to use 1.0. It's not really. If I look at this one, here is T equals 1.0. The UXS is not 0, but it's getting close to 0. So for most of the time, we just say, when capital T is 1, we're about done with settlement. Because as we know, that UXS is 0 at time infinity.